Okay, this is our very last video on equilibrium, and I do want to show you just enough to, this is going to be really quick, so I'm going to kind of power through this and just let you get your notes updated. You're going to best understand these examples by doing the problems and looking over that answer key. Again, nothing to submit, but make darn sure that you know how to do those problems. So we kind of left off here. We're about ready to talk about oxides. What can happen with an oxide? So magnesium oxide is O2, O minus 2 charge. So it's an oxygen with just that minus 2 charge. It can actually react with a water molecule to make hydroxide ions, and that of course is going to change the pH. So this is where, just get these filled in your notes here. As you're writing this out, you should see that it was a similar example that we talked about. You just break it up into its ions, and the oxide anion combines with water to make two OHs, and you can see when you combine these that those, I don't think they show that, but those two O minuses will cancel each other out, so it's just solid oxide reacting with liquid water, and there is your another example of what would seem to not really be an acid or a base, but changes the pH of a solution. Some salts can kind of go both ways and have an acidic cation and a basic anion. This is an example. Ammonium is a really good example where it has a hydrogen to donate, so it can effectively be an acid. This acetate ion certainly can accept a proton because it has lost that hydrogen on that little carboxylic acid group that's just gotten yanked off. Certainly willing to accept one back. So you got kind of a push in a situation like this. So this one, it's like, should change the pH, but wait, you have an acid and a base. So here's an example of a salt would have an acidic cation and a basic anion. This can go to form carbon or copper +1 and donating a hydrogen as it changes and goes down in oxidation number and can get reduced. Whereas hydrogen very willing to accept a proton. So again, you have a situation where they would sort of fight each other. Make sure you read through this stuff. Like I said, we're going to power through this lecture pretty quickly right here. The degree of solubility is quite important. So if you add a strong acid to an equation like this, it's one of the ways of getting these things to be able to dissolve, because you would be adding on this side, and that's just a little bit of an equilibrium shift to the right. So many times adding an acid will sort of move that compound to being more soluble. Certainly when we deal with a lot of different insoluble solids, we just add a little acid to help them dissolve a little bit better. Calcium carbonate. Now, this one's going to be a little bit tricky. Anytime you see carbonate, you're going to add that acid to try and drive it forward, and certainly that does work. However, there's one little trick. Whenever you see a carbonate, what happens is this H2CO3 right here decomposes into water and carbon dioxide. So this might be an unpredictable product, but not anymore for you, because now you know that carbonic acid, H2CO3, immediately decomposes into water and CO2, and it makes your pop bubbly. Okay, puts a little bubble in your Coke. So that's where the CO2 comes from. Actually, Diet Coke. Yeah, heart healthy. CO3 plus 2H2, you're adding the acid, sort of driving it forward again, but you also get some bubbles in there whenever you're dealing with a carbonate. So this one right here, no carbonate, so that's not going to happen. Magnesium oxide to nitric acid, a lot of you just use that in the lab. Nifty. Well, you have to wait and see what happened to our penny. We dropped a penny in nitric acid. I imagine it won't be there in the morning. Nitric acid's a good strong acid. So there's your O2, and if it's adding an acid to the O2, that will prevent that O2 from reacting with the water to form the OH, because it'll just absorb it up and make it into water. And then so what you get is a situation where, again, you're just helping this fairly insoluble magnesium oxide to shift to the right by adding an acid. And there's the chemical proof of it right there. Weak acids, going to be a similar kind of thing. So here we have our carbonate again, and if we place that in vinegar, first of all, the calcium carbonate does this a little bit, and will dissolve here. And so now when we add this weak acid over here, meaning that that hydrogen doesn't leave, but it will react with something like a carbonate ion to kind of pull that hydrogen off, because it's not really that willing to get rid of it because it's a weak acid. So there you go, and the hydrogen ends up with the carbonate, a couple of them actually, and you got H2CO3, and what's going to happen to that? It's going to turn into water and CO2. So again, this is an example of a weak acid can react with those things, and it's just now we got calcium ions where we wouldn't have had very many at all, and now you can kind of drive this reaction to the right. This you can just kind of write down. I'm not a huge fan of this, but let's finish our notes. It's interesting in terms of a pollution standpoint that iron sulfide during a mining processes was many times just kind of dumped off into the environment, and you can see it doesn't take much to react with it. It reacts with oxygen and water, and then this reaction, also not a huge fan of half coefficients. Just go through the trouble mathematically of doubling everything. But if you wanted to relate to what we're having up there, especially the iron plus 2 ions, that's why they use the 1/2 thing. But you certainly could have doubled everything up there as well. So that gets rid of the plus 2s and gets rid of half of these hydrogens over there, but you're still going to have an acidic output, and then you can end up with iron, again, complexing with those 6 water molecules and making it acidic, and the overall reaction here, this is really a nasty little byproduct. This sort of reddish solid that forms in water is often the result of pollution. So real interesting stuff, but just get that recorded and work on those problems, and just look these over and, kind of as needed for your take-home exam moving forward here. So, 10-minute short lecture is now done. Get those labs done. Work on over break and work on that take-home. And again, we'll give you a few days when you get back to polish and finish, and hopefully not start after the break. But enjoy a restful respite.